Call it in the air, heads or tails. Sometimes it'll be heads, sometimes tails. I don't know what any particular flip will be, but I do know that if I flip a coin many times, it will be heads about half the time and the other half tails. That's a pattern. In the long run, all random events have a pattern. If I know the pattern, I can predict how likely something is to happen. To look for patterns, we rely on the mathematics of statistics. Statistics is the science of collecting and analyzing data. And it touches all of our lives. Statistics is a part of our games. It helps in the search for new life-saving drugs. And it enables us to gauge people's opinions, what we think and feel about certain issues. Every day we flip a coin and try to learn from the patterns we find. We're living our chances of a lifetime.
Our high today, 61 degrees, the low 37, just 2 degrees shy of a record for the day.
Many of us get a daily dose of statistics through the media.
61 degrees, relative humidity at 36%.
We use this information to make sense of the world. For statistician Hal Stern, statistics helps him to track his favorite baseball teams, to see the game behind the numbers.
I always liked numbers. I was the kid who played with his calculator more than was probably good, and always interested in sports. And thinking back now, I realize it's probably for the numbers. I was the guy on the Little League team who computed people's batting averages and the like. One of the things I like about all sports is that seems to me anyway, to be uncertainty kind of at its finest. Baseball is a fine example. The uncertainty is there, and there's also a long history of keeping track of records and numbers and averages. And it's a wonderful place to play.
Numbers and averages are important to statisticians, and baseball is filled with revealing data.
When I think of baseball statistics, I think of batting averages and won-loss records and pitchers' earned run averages, and those are what I like to think of as small s statistics.
In baseball, small s statistics are used to track players' performances. And some small s statistics are legendary. Hank Aaron's record of 755 home runs is a small s statistic that has stood for more than 2 decades.
Out of here! It's gone! It's 715! The home run champion of all time!
Cal Ripken entered the record books by playing in 2,131 consecutive games. That's a streak of 13 straight years. Nolan Ryan has amazed baseball fans with an incredible small s statistic. He has pitched 7 games in which no player has gotten a hit.
Small s statistics, they're numbers, and they're interesting. But the field of statistics, or capital S statistics, is more about drawing conclusions from those numbers.
In baseball parks across the country, the person responsible for making decisions based on statistics is the manager.
The manager in baseball has the role, in some ways, that the statistician would want. He knows his players and their abilities, and is faced with situations every inning about where decisions have to be made.
Hal Stern is a fan of the Iowa Cubs, a Triple-A team for the Chicago Cubs, one step away from the majors. The Cubs manager is Ron Clark. For 9 innings, Clark will rely on statistics to evaluate and make decisions about his team and the game.
Your 1995 Iowa Cubs.
This process of analyzing data to draw conclusions began more than 1,000 years ago, half a world away. England, the Middle Ages. William the Conqueror is presiding over a vast kingdom, a collection of wealth he actually knows very little about. To assess his kingdom, he assembles an army to gather data.
William the Conqueror wanted data on all of England, and he sent around his data gatherers. They divided up the country into small areas and asked of each area how many people were living there and what sort of agricultural products were coming from there. This, in a sense, was a beginning of statistics, but there was no real statistical analysis at that time. It was simply a tremendously ambitious data gathering operation.
This collection of statistics provided William the Conqueror with an assessment of his kingdom and wealth. The text was named the Doomsday Book, but the real power of the book would not be recognized for another 500 years. By the middle of the 17th century, England had grown, but nobody really knew the size of the population. According to popular belief, England's largest city, London, was home to more than 2 million people. To one London resident, this was idle speculation. John Grant believed that he could deduce London's true population by using data from the Doomsday Book.
Many statisticians and historians of statistics date the origin of statistical thinking to John Grant. John Grant was not an academic. He ran a store. He was a haberdasher. But he got hold of these records and began looking at them and was able to do some rather remarkable analysis.
By studying the stats in the Doomsday Book, one piece of information got Grant's attention. On average, it appeared as if there were 10,000 christenings every year. Using this small s statistic, Grant began to make some inferences. Grant reasoned that if there were 10,000 christenings, this would be closely related to the number of births. The number of births relates to the number of women of childbearing age. The number of women relates to the number of families and their size. Through his calculation, Grant determined that England's population wasn't 2 million, but rather 1/5 that size, or 384,000. Most experts today believe Grant's estimate was very close to the true numbers. By drawing conclusions from data, Grant began modern statistical analysis. Back at Sec Taylor Stadium, manager Ron Clark is faced with his own set of numbers to consider. It's late in the game, the bottom of the 6th inning, and Clark's team is behind 2-1. Clark's first batter gets on base. With no outs and the tying run on first base, Clark needs to develop a strategy to advance the runner. He considers a sacrifice bunt. In a sacrifice bunt, the batter bunts the ball in front of the plate. The batter will probably be thrown out as the sacrifice. The bunt, however, enables a runner to advance. On the surface, this looks like a good choice. However, Clark considers several other statistics. On the mound is pitcher Steve Olson. One of Olson's small s statistics is very telling. He has a high earned run average of 4.57, which means he gives away an average of more than 4 runs per game. Batting next against Olson is outfielder Brooks Kiesnick, who has a good batting average. As does third baseman Matt Franco, who is on deck. With 2 batters coming up with good batting averages against a pitcher who gives away a lot of runs, Clark makes a decision and signals his batter. In this case, Clark's decision pays off. The tying run has advanced without sacrificing an out.
Baseball managers, I think, have a very difficult job. Deciding whether to bunt or who to play on a particular day depends on the manager's decision. The decision-making is hard because you don't know what's going to happen, and you're making decisions based on what are going to give you the best chance of success.
On this day, Clark's strategy for the Iowa Cubs works, and they win 6-5. A victory built on athletics and statistics. Statistics are a big part of all the games that we play. And when it comes to games of chance, casino owners are banking on the numbers. Billions of dollars are generated every year by the gaming industry. And much of that fortune relies on a part of statistics called probability theory.
Probability theory is a system to look into the future. If you want to look into something that's going to happen tomorrow or next week, there could be a whole range of things that's going to happen. What probability theory lets you do is say, this is most likely to happen, that thing's most likely to happen, or that thing's most likely to happen. It allows you to take a whole range of possibilities and narrow them down.
The mathematics of probability was actually developed as a way to understand games of chance. Look just beyond the glitter and the lights, and you'll see mathematics. Edward Packle knows all about probability and the games of chance.
One of my administrators did ask me many years ago what gambling had to do with mathematics in the sense that I was proposing to teach a course on the mathematics of games and gambling. And after discussing with them the historical importance of gambling as a source of the original ideas, or many of the original ideas of probability theory, they were convinced that it had a lot to do with probability and mathematics and logical thinking.
Since ancient times, we've been trying our luck at games of chance. In fact, some of the first dice were actually made from the ankle bones of animals. For centuries, luck was the name of the game. Nobody was understood to have an edge. But then in the 17th century, two mathematicians changed everything.
Blaise Pascal and Pierre de Fermat were two of the most famous mathematicians of the 17th century. Pascal had a colleague who was a keen gambler. The gambler came to Pascal and said he wanted to know the answer to a certain question about probabilities to do with playing gambling games.
The problem that piqued Pascal and Fermat's interest revolved around a game of dice that comes to an untimely end.
Suppose two people are playing a game. They're gambling with each other, and halfway through the game, they have to abandon it. One person is ahead of the other person at that stage. Question, how do they divide the pot so that it's fair to both? Now, if you think about it, that means you have to look into the future, the potential future that would have happened had they been able to complete the game.
In a series of letters, Pascal and Fermat imagined a game of dice to be played in 5 rounds. The first person to win 3 rounds wins the game. In their scenario, they imagined that Fermat was ahead 2 rounds to 1. Fermat just needs 1 more round to win. Next, the mathematicians looked at all the possible outcomes. For example, if Fermat won rounds 4 and 5, he would win the game because he would have won at least 3 of 5 rounds. If Fermat won round 4 and lost round 5, then he'd win again because again, he won 3 of 5 rounds. If Fermat lost round 4 and won round 5, he'd still win. In fact, the only way for Fermat to lose would be if he lost both of the last 2 rounds. Given these possible outcomes, Fermat and Pascal correctly reasoned the odds were 3 to 1 in favor of Fermat. Therefore, Fermat should get 3/4 of the pot and Pascal 1/4. The mathematicians calculated how a slight edge would result in one player winning more often than not. More than 300 years later, casinos like this one profit on the laws of probability.
The odds of winning in a casino are very, very small. In general, with every game, the odds are stacked against you, which does not mean that no one will win, but it does mean that any individual who plays for a reasonably long amount of time and repeatedly is almost surely going to lose. The reason the casino has a built-in edge is that every game is carefully constructed so that if you do the mathematics of it, it turns out that the casino will have a favorable expectation for winning.
The game of roulette, for example, relies on the laws of probability. The roulette wheel consists of 38 slots. There are 18 black slots, 18 red slots, and 2 green slots. If you place a bet on black, you have 18 chances of winning. But you have 20 chances of losing. The odds are stacked slightly against you. The house will win 53% of the time, and that small edge leads to large profits.
When I first started thinking about a good way to explain why casinos make money, the first thing I thought of was something called a Galton board.
With this Galton board program, Paco sets up the simulation to represent a series of bets where the odds are even.
And what we have now is a bunch of coins are going to drop from the top here, and think of yourself as a bettor as one of those coins. And each time you hit one of these pegs, you will move left or right with 50-50 probability. If you move left, let's think of it as meaning that you've lost, left for lost. And if you move right, then you win. And then you're going to bounce down to another level of pegs, and altogether you're going to make 10 bets. And you'll win some and you'll lose some, and we'll see where you end up. So we'll step through this one step at a time. So the first bettor won, then lost, won, lost, won, won, lost, won, lost, and ended up breaking exactly even. Let's speed it up a little bit. And now we're going to have 256 people all doing the same thing you just did, and we'll look at what the results are. And what we have is something that very much approximates a bell-shaped curve. In fact, it's approximating what's called the binomial distribution. And notice that the result of breaking even happens to be the most likely of these results, but there are many more results clustered around the middle and many fewer results at the extremes. Casinos in this situation would not make very much money. Let's go back and reset the simulation, and let's change the probability from what it was to 53% in favor of the casino. That's very much like what it would be in roulette, where the probability of winning on any of these even money bets is essentially about 53% for the casino and 47% for you. So we're going to make that small change. As I said, the odds are only slightly in favor of the casino, but let's see what happens. But notice that the center of the curve, the peak, has shifted to the left. This is very important for a casino. That means that there are still some people. Here's an individual out here who won 6 more than they lost. There's lots of people who were in the middle, but by and large, the losses have shifted to the left. The curve has shifted to the left.
By slightly skewing the odds, casinos rack up profits of over $16 billion every year. For most people, the real power of probability theory comes when mathematicians take it out of the gambling hall and into everyday life, which was something Pascal and Fermat never imagined.
It never seems to have occurred to them that when they developed this mathematical technique that allowed them to look forward into the future, that you could take it away from the gambling tables and use it in other areas of life.
One of probability theory's greatest powers is that it can help us to gauge public opinion. And this touches all of our lives.
The stakes are very high for this institution because once again, the American people will be asking if we can govern.
Politicians rely on public opinion to keep track of their constituents' values.
Our major economic asset is our people. All of our policies, therefore, must be people-focused.
Public opinion influences what we see on television. And what we find in the supermarket.
Virtually every facet of our everyday lives, to some extent, is influenced through public opinion.
What is it they make Dodger dogs out of?
New products are tested, typically through surveying techniques. Also, public opinion polling, to a large extent, determines what it is that we see on TV.
Do you want milk or yogurt?
Okay, what'd you get?
Cherry vanilla.
Cherry vanilla? I gotta have peach.
We're interested typically in this country in knowing what a majority of the people feel. That's behind our basic political structure. That's how it is. You go about calculating it, and then the way I interpret this information statistically is I tack
in the
on
classroom,
a margin of
Kay
error
teaches
to the point
opinion
estimate.
polling.
If I subtract 6% from this, I get 69%.
But in the classroom, the true power of probability isn't always obvious.
What amounts to is the amount of information you obtain. I went through a number of theoretical techniques, derived a lot of formulas and this and that, but I always wondered, does this stuff really work in practice? Now, what's the next one of these things I can do in my head?
To test theories of probability, Kay established his own public opinion polling business, which he runs from his home. His wife, Gary, is the other half of Kay Associates.
No, this is my stuff.
We have been in the public opinion polling business for about 10 years here in El Paso. We kind of work as a team together. Okay. What a public opinion poll will do is actually quantify how it is that a particular body of people feel about a particular issue at a particular time.
A public opinion poll can enable Kay to understand what the more than 500,000 residents of El Paso are thinking. Amazingly, he can gain this insight by just gathering the opinions of a small group. According to the laws of probability, a small representative group will accurately reflect the opinions of a larger society if the participants are chosen at random.
How many of these do I have to do?
Selecting the respondents or potential respondents in a scientific survey is very much like trying to get a representative sample from a large container of minestrone soup.
It smells good.
First thing I want to do, and this is where the randomization comes in, just as it does in a scientific public opinion poll, you want to make sure that the pot is thoroughly stirred. Okay, we stir it, reach in, and pull it out. This gives me a pretty good indication of what the ingredients are in the minestrone. I look at it, I see I've got sausage, I've got carrots in here, I've got green beans, I've got kidney beans, and I've got some onions in here and also some celery. So by thoroughly stirring the pot, I was able to get a representative sample of what the soup ingredients are. Just to illustrate the importance of the mixing, what I'm going to do is now reach in and just pull out a sample from the top, and I'll see how representative that is of the soup ingredients. Well, the scoop size is still the same. I've got the same size sample, but I don't have a thorough mix, so I don't end up with a representative sample.
When pollsters scoop out participants, it is essential that they start with sample groups that are truly representative. If the group is not representative, no amount of mixing and scooping will help. The poll will be misleading. For example, one of the biggest blunders in polling involved one of the largest polls in history. In 1936, the Literary Digest magazine polled 10 million people and predicted that Republican Alf Landon was going to be the next president of the United States. The fact that you might not recognize Alf Landon's name is a good indicator that the poll was dead wrong. The problem with the Digest poll arose from the techniques used to create their sample group. For starters, the Digest relied on various lists, and the lists were not representative of the population. For example, lists derived from the phone book left out people who didn't have phones. This was a large part of the population in 1936. Membership lists from country clubs excluded poorer participants. That same year, another pollster, George Gallup, was getting his start. Gallup chose lists that truly represented the population. To ensure an accurate mix, he then chose 50,000 people at random, which is less than 1% of the size of the Literary Digest sample. Because Gallup relied on sound sampling techniques, his results were more accurate. Gallup predicted that Roosevelt would be victorious by a landslide. And the rest is history. For both men. Polling is a critical element these days for every election. And before the mayoral election in El Paso, Bill Kay performs a series of public opinion polls. To establish the sample for his poll, Kay begins with the list that reflects El Paso's diverse population. This is like his large pot of minestrone soup. Next, he uses his computer to randomly scoop a group from the list.
A lot of people have a difficult time in conceiving that it's possible by taking a relatively small sample on the order of hundreds, you can actually make a generalization about a population, say, of perhaps even millions. It's always very interesting to me. I really get a kick out of finally when this is all the effort's been done, I can actually tabulate the numbers and see what the poll showed.
By relying on good polling techniques, Kay is able to predict the outcome of the El Paso mayoral election. And to the surprise of some, what was perceived as a horse race turns out to be a landslide.
Okay, this is hot off the computer, all 309 respondents.
Live from the news station. This is News 7 at 6.
Now here's a look at the actual numbers from the El Paso Times News 7 poll that led Carlos Ramirez to his decision
Dr.
today.
Fink at 7%. Carlos Ramirez, 14%. Mayor Francis, 71% of the people are going to vote for him.
Larry Francis is their choice for mayor.
So call up his honor very quickly and be nice to him.
While probability is critical for creating an accurate random sample, one of its greatest powers is that it helps us to assess the value of results. And this power, as you'll see, is helping in the battle against disease. Over $14 billion is spent yearly in the United States on medical research, and often the results are dramatic.
For the first time, researchers are saying they have evidence that AZT can actually prevent the spread of AIDS.
In the search for new drugs, we turn to probability. Probability helps us to determine the safety and effectiveness of new medicines.
Scientists say the new test should be a great help in finding better treatments or a cure.
Susan Ellenberg is a division director at the U.S. Food and Drug Administration. Her department designs and evaluates studies of new vaccines. She remembers what was possibly the most famous application of statistics to fight disease, the polio vaccine trials of the 1950s.
I ran the numbers, but I'm not sure that I did it right.
Anybody who was around back then will remember there was enormous concern. Everyone was very fearful about polio. People wouldn't let their kids go swimming. It was one of the most fearful diseases.
Between 1916 and the 1950s, something mysterious and terrible was happening to America's children. Without warning, infants and young people would begin to experience excruciating muscle pain and stiffness in the neck. Those afflicted by the symptoms might lose the use of their limbs or become paralyzed. In some cases, they might even die. Polio, as the disease was called, claimed many hundreds of thousands of young victims in the United States. And with the baby boom, the epidemic threatened even more harm.
In a way, this was a time period when American society was very closely attuned to polio as a problem. After all, it was the post-World War II era. There were a massive growth in the number of children being born in America and a concern about their health and safety.
In Pittsburgh, Pennsylvania, a city of smoke and steel, there came a glimmer of hope. Dr. Jonas Salk believed he'd found a vaccine, and he set out to test his medicine. To ensure that his tests were accurate, Salk relied on careful statistical methodology. In 1954, 1.8 million school children would partake in the trial, the largest of its kind in history. The children were separated into two groups at random. Because of the random assignments, the laws of probability practically guaranteed that the two groups would be nearly identical, and that sameness would help Salk track the effects of his new drug. For example, if Salk did nothing and just watched the groups, according to the laws of probability, both groups would come down with roughly the same number of polio cases. If, on the other hand, Salk gave one group his vaccine and they had fewer cases of polio, this might mean that his drug worked, and probability would help him to gauge its effectiveness.
You needed to have children treated at the same point in time and be able to say, did the group that got the vaccine have fewer cases of polio than the group that didn't get the vaccine?
As the Salk trial progressed, it did appear as if the group that got the vaccine had fewer instances of polio. To be certain the success rate was due to the drug and not just chance, Salk's data was subjected to statistical analysis. To assess the data, the researchers focused their attention on the total number of polio cases reported in both groups. If the difference between groups was small, so small that it could be mere chance, the vaccine would be found not to be effective. As the researchers tabulated the data, they found that the differences were so great that they could not be attributed to chance. The vaccine had proven an overwhelming success.
In many ways, I think, the Salk development of the vaccine represents an ideal, a high point of both the faith in medical science and the ability of medical science to produce. And in a way, I think ever since the 1950s, medical science has aspired to that ideal of the Salk vaccine trials.
Today, clinical trials are conducted at the National Institutes of Health Clinical Center in Bethesda, Maryland. Over 900 trials are conducted here each year. Just like the Salk trial, participants are assembled into groups. Today, random numbers are used to decide who gets a drug and who gets a neutral substance, called a placebo. Doctors are still responsible for monitoring and recording the well-being of their patients.
That's right, it doesn't turn around all the way.
But the true key of a drug's success will be derived from the numbers.
The FDA, in deciding whether a new drug or new product can be approved, needs to see the data. We have to say, show me your results. Show me that you did a valid study, and show me that the results really show, one, that this product is safe, and two, that it works.
Under the power of statistical analysis, we can develop new drugs to help battle disease. Statistics can also be used to protect us in the face of uncertainty. Grant Steer knows a few things about uncertainty. He uses statistics and probability to calculate the odds and risks in the game of life. Steer works for Fireman's Fund Insurance, one of the oldest insurance companies in the world.
One of the most obvious applications of probability theory these days is the insurance industry. You want to go out and you want to take insurance on your life or on your car. What you're doing is you're finding someone who's prepared to take a bet on your car not being damaged or on your life not coming to an end.
Probably fall in the $150 range. We do have a bit of weather coverage under this, you know, the hurricane preventing.
At Fireman's Fund, Steer is an actuary.
So we can assess the costs of each of those coverages and make some assessment of what the frequency of each of those coverages might be.
Actuaries in general are most likely involved in setting rates, trying to charge or be able to decide what the price ought to be for the policies and the products we sell.
What kind of things can go wrong, Sue?
Today, Steer and his colleagues are trying to assess the cost and risk of a new and unusual policy, wedding insurance.
If the wedding site goes out of business, how do we determine a rate for that?
We're only refunding
if the wedding does not take place.
Right, if they decide to cancel because of critical guests not appearing.
What we need to be able to do is to charge a price that covers the average loss for all. Insurance usually has a history of the data from the types of losses that the particular policy they've sold has covered, so they've got some actual statistics on the types of losses that we've incurred. For wedding insurance, it was a new coverage.
In the case of wedding insurance, the first step is to research the cost of various wedding elements. Sue Lim and her colleagues are trying to determine what things to insure. Wedding attire, wedding photographs, wedding gifts.
Oh, hi, Wayne. I was just calling to inquire about the rates for your wedding portraits. Can you give me a price range?
Each year in the United States, there are over 2 million weddings. And according to Bride's magazine, the average cost is between $15,000 and $20,000. For many families, a wedding is a huge investment of time and money.
Okay, there's Tim, there's the marriage license you haven't got, that you don't have yet.
Chad and Adele Smith remember their own wedding day.
Picture, Adele.
This would have been nice.
They are hoping and planning for just such a special day for their daughter Rochelle and her fiance Tim.
Nothing in them. There's a lot of things that you don't really get a chance to do over again. So you have to make sure that when you plan these things, it's planned right the first time. So we take time and try to do it right. Yeah, Adele threw her bouquet into the band.
Yeah, the band got it. Your big investments in life are your home, your cars, and a wedding. I mean, I would think that a wedding rates right up among those two things. What else do you do that costs so many thousands of dollars? And to not insure it, you wouldn't think of not insuring your car or your home. So why not the wedding?
At Fireman's Fund, Grant Steer is beginning to determine what elements to insure. In the policy, they can insure wedding cancellation, photographs, wedding attire, wedding gifts, and personal liability.
All of these different pieces that are associated with a wedding, we added up as best we could what the costs of the various insurable losses were, and the other thing we'd need to know is how often did these losses occur.
Get your error to be less than 165.
Grant consults with actuary Bob Butzik to try to predict the frequency of wedding cancellation. Just one element of a wedding that needs to be considered.
You were down to 21 here before. I don't know what you're trying to maximize now.
For cancellation insurance, we knew that the longer an engagement lasted or the longer a policy was in place before the actual wedding, there were more chances, more opportunities for things to go wrong.
So couples with long engagements are riskier for the insurance company than couples with short engagements.
The alpha is the what?
We didn't think we could charge a different premium over a short engagement versus a long engagement, or a short policy term before wedding versus a long policy term. So to simplify the rating, we decided to average over those different frequencies or numbers of claims per policy that might occur. We had some idea of what these coverages were. We checked them out as best we could with available reference material or available experts in the field to help us firm up our estimate of what these costs might be. And if they could tell us what they thought the number of these types of claims might be, or how often they would happen, that would give us the fundamental components into what this wedding insurance policy ought to cost. Our assumptions are that we'll have, in general, about 3 claims per 100. So about 3% of the time we're going to have a claim.
Because of this low risk, the insurance company is able to provide Tim and Rochelle thousands of dollars worth of coverage for a policy premium that costs a little more than $100.
Okay, let's try to get a photo.
The insurance company is counting on things going right, but there's still a 3% chance that something might go wrong.
A cousin of mine at a wedding a year ago, and there was a problem with her photographer, and they had a problem with getting their pictures done, and it was a really sad thing because a lot of their pictures didn't turn out, and she missed a part of that. And so we thought, well, we don't want anything like that to happen, where we want to have everything perfect. So this is a little bit of a safety net.
I really don't think that there's anything you can do to give you total peace of mind when you're planning for your only child's wedding. But just knowing that if something happened to the bridal gown or something happened at the reception. It gives you some feeling of like, well, maybe we can do this if something terrible happens. But
again, you hope you never have to use this insurance. It's just like everything else. Insurance is fine, but you don't ever want to use it.
I'm very happy to present to you Mr. and Mrs. 17 Simon.
The Smiths' wedding comes off beautifully as planned. And they didn't have to use the insurance safety net.
There is no absolute truth. There is no roulette wheel to tell us how often a 1 or a 2 or a 3 is going to come up. So we're always having to make estimates from the information we have, from the data we've been able to gather, from our common sense or our view of the world. We're trying to make predictions of the future.
No one knows what the future holds. But by using statistics and probability, we can begin to discover useful patterns.
In a way, probability helps you to put some kind of a pattern on randomness. You can't tell what's going to happen from step to step, but you can predict what's going to happen over the long haul.
By uncovering patterns, we can better evaluate new life-saving drugs.
Small number, it's a pretty big difference.
We can gauge the opinions of the masses and get a handle on the uncertainty that touches all of our lives.
Being able to handle uncertainty, which basically is what probability is, or what statistics is about. That's always been just very fascinating to me, to be able to foretell the future.
Predicting the future helps us to make decisions about the present. And making decisions, evaluating information, is at the heart of statistics.
Information and decisions gets at what we try to do. People think naturally of the numbers, and less of what I think the interesting part is, using the numbers to make decisions about everything under the sun.
To learn more about the Life by the Numbers series, visit PBS online at the internet address on your screen. Exclusive corporate support for this program comes from Texas Instruments.
Texas Instruments is proud to partner with the education community to create the calculators that help children do extraordinary things. Because the more our children can get out of math and science, the more they'll get out of life.
With major funding from the National Science Foundation. America's investment in the future. And the Alfred P. Sloan Foundation to increase understanding of the application of mathematics in everyday life. Additional funding provided by the McDonnell Douglas Foundation and the Alcoa Foundation. To order a video of this program, other programs in the Life by the Numbers series, or the companion book, please call 1-800-274-1307 or write to the address on your screen.
This is PBS.